So the first step in both of the previous examples was to ask whether or not these two partial derivatives are equal. And it turns out that this is such a common occurrence that we're going to give this thing, this sort of object, a special name. But first we're going to rewrite it in a different form. Let's subtract the partial of f1 with respect to y to the right side. And remember that our question was always, are these equal? Well, that's the same as the difference of these two partial derivatives being equal to 0. And this quantity turns out to be very important. We're going to call it the curl of the vector field f. So in particular, notice if the curl is not equal to 0, then the vector field f is not a gradient field. And we'll get to the converse a little bit later, but there's one slight twist. So here's why the curl turns out to be so important. I'm going to leave out the proof right now. It would take too much to put it in a video, but you're welcome to ask me about it. So here's the idea. If I have a closed curve, and this curve needs to be nice, so in particular it shouldn't be too bendy and it shouldn't cross itself. If it crosses itself, then simply split it up into several different curves. Second, you always need to orient the curve in a particular direction. So if this is the closed curve C, I always want the region, the region that's bounded by the curve to be on the left. So I need to orient the curve going such that as I walk around, the region is on my left-hand side. If you don't do this, you'll be off by a sign. So just make sure you do that. And then one more condition. The vector field, just like the curve, has to be nice. And this is where the twist that I mentioned a minute ago comes in. It has to be nice both on the curve and inside the curve. And you really need to be careful because there are examples where this doesn't hold. If it does hold, then we get Green's theorem. This is Green's theorem. Green's theorem says that I can evaluate the line integral around this curve of this nice vector field by integrating, and this is no longer a line integral but a double integral, integrating the curl of f, which is not a vector field, over the region R. So dx dy describes the region R. So again, what Green's theorem does is it turns a line integral into a double integral, or if it's convenient, turns a double integral into a line integral. And this gives you a way to choose which one is easier to evaluate. Here's an example. We'd like to evaluate the line integral of the vector field f dot dr, where this is the vector field, and C is the closed path which goes around the triangle from 2, 0 to 0, 3 to minus 2, 0 and back to 2, 0. So we've done examples like this before, and you'll remember that what we needed to do was to parameterize every one of these paths and to evaluate 3 line integrals using the parameterization of the paths. So you're gonna see in just a second that Green's theorem provides a much easier way to do this. So first, let's calculate the curl. So the curl is the partial of 2x plus 3y squared with respect to x minus the partial of 2x squared 3y plus 3y with respect to y. And notice that this is particularly nice. The derivative with respect to x of the first term is simply, of 2x plus 3y squared is simply 2, minus the derivative with respect to y of this term is 3. So I simply get minus 3, and the curl then is minus 1. So the line integral is equal to the integral around this region. The region R is the region inside the triangle of the curl, which is just minus 1, dx dy. Okay, so let's just check a couple things before we finish. Notice this vector field is defined everywhere. There are no holes inside this triangle. As I walk around the triangle, the region is on my left-hand side. So we're set to apply Green's theorem. And notice that I can pull out the minus 1, and I simply have the integral around the region, or inside the region dx dy, but that's just the area of the triangle. So this is minus 1 times the area of the triangle, and I know that the area of a triangle is 1/2 times the base. The length of the base is 4, times the height, and the height here is 3. And let me scribble out that equals. So it's -1 times the area of the triangle. The area of the triangle looks like it's 6, and so the value of this line integral is -6. Okay, so Green's theorem allows us to complete the argument from before. So before, we had that if the vector field f is a gradient field, then it must be that the curl is 0. So it turns out, though it's a little bit more work to show, that the converse statement is also true. So that is, if the curl of f is 0, and this is an important and the vector field f is nice, that is, it has no holes, it's defined everywhere, then it turns out that f is a gradient field. So if I can check these two things, then I know that f is a gradient field. And let me just remind you that if it's a gradient field, that means that it's path independent, and that it means that I can find a potential function. This issue of holes, I'll do a couple examples on another slide where I illustrate what happens when there are holes in the vector field and why this and Green's theorem falls apart. And finally, let me mention, though I'm not going to put anything here, obviously, there's also a curl test for vector fields that live in 3 space, so those that have I, j, and k components. And I think we're going to hold off until chapter 20 and come back to that.